Hi there, in this video we're going to learn move logical instructions. We'll start with move and mask move instructions. Then logical bitwise instruction will be explained. Also, we'll see what are swap byte, clear, and bit field distribute instructions. Finally, we'll do a simple project, using these instructions, to turn on 8 fans of 8 industrial cabinets. My name is Syed Reza, and before we get started with today's video, I just wanted to inform you about all the great content I have been releasing on the PLC Goods YouTube channel, which includes industrial automation PLC programming, HMI and microcontroller-based developments. If you enjoy this video, I would appreciate it if you could click the subscribe button as well as the notification bell to receive the latest and the greatest content I will be posting through the channel. Alright, I'm using this virtual PLC station, which can be created by RSLogix Emulate 5000 software. Also, I've configured that inside the programming software, RSLogix 5000. Now, I want to explain move and logical instructions. The first instruction is move. This instruction copies the source value to the destination address. Note that the source value remains unchanged. That's simple. Try to test it. Let me explain the next instruction. MVM, or mask move instruction. Similarly, this instruction copies the source value to a destination address, but it uses a mask value to determine which part of the data should be copied. For example, suppose, here is a tag with name A, which its data type is short integer. This data type uses 8 bits, to store numbers from -128 to 127. The A value should be copied to the destination address. But here, we can determine which bits of these 8 bits can be copied. So, let me enter the mask value in binary form. Here I want to copy bits number 4 to 7 of tag A. If I want to use the MVM instruction, like the move instruction, it means all bits should be copied. In this case, all 8 bits must be 1. Let's store the result on the B tag, which its data type is short integer 2. Now, let me download the program to my virtual processor. Well, I must change the processor mode to program mode. Let's open the program tags table, to see values of the A and B tags. Here, I'm entering a value in binary form, but its value is displayed in decimal style. To see a number in binary form, I must select the desired style in this column. As you can see, based on this value, only bit numbers 4, 5, 6, and 7 of the A tag will be copied to the B tag. Let's open the help window, and search the MVM instruction. Here you can see a complete description of this instruction. As you see, here is an example, when the entered data types are double integer. A double integer uses 32 bits to store numbers. In this example, this is the destination value, the tag with name value _b, before using this instruction. This the source value, and this is the mask number. Based on the mask number, only these bits will be copied from the source value to the destination address, and other bits remain unchanged. Note that you can search for data types to see all data types and their properties. For example, here we can see the range of short or double integer data. Or select another data type to see their details, like counter structure, which has been explained before. Here, you can see what happen if a real number save on a tag with integer data type. Alright, after the move and mask move instructions, there are 4 instructions perform bitwise logic operations. These instructions are bitwise and, or, exclusive or, and not. Let's have a short review of the basic logics. Note that, to activate or inactive a bit of PLC memory, I can right-click on a contact and select toggle bit, or use Ctrl+T on my keyboard. Well, as you maybe know, the first rung represent AND logic. The output will be on, if and only if the S1 and S2 are activated. The next rung represents OR logic. The output will be on, if S1 or S2 or both of them are activated. To turn off the output, both S1 and S2 must be inactivated. The rung number 2 represents exclusive OR logic. In this rung, the output will be on or true, only when inputs differ. One contact is true, and the other one is false. Finally, the rung number 3 represent the NOT logic. As you know, the output will be on or true, if the S1 tag be false or 0. Now, let's see how the bitwise exclusive OR instruction works. Other bitwise logic instructions can be tested similarly. When this instruction is enabled, it performs a bitwise XOR operation on source A and source B, bit by bit, and places the result in the destination tag. As I just said in the third rung, when the exclusive logic is used, the output will be true only when inputs differ. So, based on the source A and B values, the output will be this. Note that, here we see the result in decimal form. To see that in binary form, let's go to the program tags table. Alright, the next instruction is swap byte. This instruction rearranges the order of the bytes of the source. It places the result in the destination. Well, this instruction rearranges the bytes of a value. Suppose the source value be a double integer number. So, it has 32 bits. Assign letter A, B, C and D to each 8 bits as this way. The swap byte instruction can arrange them differently. Now, if you want to change the bytes to this pattern, I must select reverse in the order mode parameter. So, based on the selected mode, the result will be a double integer 2, with this value. This instruction has 3 order modes: reverse, word, high-low. Here, you can see an example of each 3 order modes. Alright, after the swap byte instruction, the bitwise NOT instruction works like the XOR bitwise. The clear instruction clears all the bits of its destination address or tag. That's simple. If you remember, we have used that in the previous video. Now, let me explain this instruction, the bit field distribute. Well, this instruction copies the specified bits from the source value, shifts the bits to the appropriate position, and then writes the bits into the destination address. As you see, this instruction gets 5 parameters. Let's learn how this instruction works using an example. When the BTD instruction enabled, it copies a group of bits from the source value to the destination address. The group of bits is identified by the lowest bit number of the group, source bit, and the number of bits to copy, length. The destination bit identifies the lowest bit number in the destination address. So, the selected bits will be copied on these bits of the destination address. Note that, if the length of the bit field extends beyond the destination address, the instruction does not save the extra bits. Also, the source value remains unchanged. Alright, I have explained move logical instruction. Now, let's define and do a simple project. Note that, here I have a virtual input-output module, which has 32 inputs, and also 32 outputs. Now, let me define a project. Here you can see an industrial cabinet with its fan. I want to write a PLC program to turn on this fan. Usually, there are some electrical devices inside the cabinet. Suppose it has a door limit switch, a temperature sensor, and a start push button which have connected to a PLC with this diagram. In this project, I use my virtual processor. When the cabinet door is closed, this limit switch will be closed too. So, the voltage will reach the PLC input module, and the related input address will be true in the PLC program. The temperature sensor is connected to the PLC, using its normally close contact. So, when the temperature is higher than a specified value, for example 30 degrees centigrade, this contact will be open, so the voltage won't reach the PLC input, and the related input address will be 0 in my program. Like the door limit switch, if this push button is pressed, the voltage will reach the PLC input module. So, its related input address will be true in the PLC program. This program can turn on the fan. Based on this program, when the temperature is higher than 30 degrees, the related input address will be 0, so, the state of this normally close contact won't change, and it will pass the virtual power in my program. If the push button is pressed, its related address will be 1. So, the state of this contact will change to close, and pass the virtual power in my program. Similarly, when the door is closed, this contact will pass the virtual power. So, if the temperature is higher than 30 degrees, or the push button is pressed manually, and the cabinet door is closed, the fan will be turned on by the PLC. Note that, in this program, here is an OR logic, and after that, there is an AND logic. Now, suppose there are 8 cabinets, and we need to turn on their fans based on the previous program logic. Naturally, 8 digital inputs must be considered for limit switches, temperature sensors, and push buttons. Also 8 digital outputs are needed to turn on 8 fans. Note that, the previous program can be repeated 8 times, but let's write the PLC program using move and logical instructions. First, I use this bitfield distribute instruction, to move the first 8 digital inputs, to the first 8 bits of a PLC memory. I use a tag with this name. Limit _ switches as the destination address. Note that its data type is double integer. This data type has 32 bits, but only its first 8 bits will be needed, which store the state of 8 limit switches. Similarly, in the next rung, I use a bitfield distribute instruction, to move the second 8 digital inputs, to the first 8 bits of a PLC memory. These digital inputs are connected to the 8 temperature sensors. So, I need a bitwise NOT instruction to inverse them. Like the normally closed contact, which has been used in the previous slide. Well, in the third rung, I use another bit field distribute instruction, to move the third 8 digital inputs, bit number 16 to 23, to the first 8 bits of a PLC memory. Here, I use a tag with this name, Pushbuttons, as the destination address. Because these bits represent 8 pushbutton status. Now, I can use Bitwise logic instruction to write the explained logic control in one rung, instead of repeating the explained logic, in 8 lines. Well, I need a bitwise inclusive OR, and a bitwise AND instruction. Alright, I save the final result on this tag. Variable 2. But only the first 8 bits must be transferred to the first 8 bits of the analog module. So, I use mask move instruction. Here, I enter the masked value in hexadecimal form. Based on this number, only the first 8 bits will be transferred to the output module, which 8 fans are connected to that. Now, let's download the program to the virtual controller. Let me open the program tags table. Also, I must change the controller mode to run mode. Note that, in the normal conditions, these inputs are activated by the temperature sensors. As you see, the defined tags have 32 bits, but the first 8 bits will be needed in this project. Alright, suppose only the first 4 cabinet doors are closed. As you see, the first 4 cabinet fans can be turned on, if I activate their push buttons, or inactive its temperature sensors. Doors of the next 4 cabinet are open, so, their fans cannot be turned on by pressing related push buttons or inactivating related temperature sensors. Alright, this program can be extended to 32 cabinets easily. It only needs to modify the mask number in the program. In the next video, we'll continue learning RSLogix 5000 instructions. Thanks for watching my content. If you have any question on this topic, make sure you leave them in the comment section below, and if you can spend a few seconds of your time liking as well as sharing this video, if you enjoyed it, that will mean a lot to me. If you have any suggestions for the channel, such as what kind of hardware or software I should be covering, then make sure to leave that in the comment section. See you next time. Bye bye.